Very good morning to all. Today we are discuss about wave equation. So wave equation means neglect classes, less complex algebra. L, C parameters per meter. The diagram will be represented for input side voltage, input voltage, then inductance, then change in inductance, then capacitance, change in capacitance. Then del x means then distance. Then V plus del V means change in voltage, normal voltage to change in voltage. Voltage across the element del x, V minus V plus del V. Supply voltage minus change in voltage is equal to minus change in voltage is equal to L del x dou I by dou t. As del x 0, we get dou I by dou x is equal to minus L dou I by dou t. That means change in magnitude. Partial derivative because V and I are function of position x and time. Dou I by dou x and dou I by dou x derived later. Equations called telegraphy equation. There are also called wave equation. Here we will refer to the equation, a first order wave equation. Current to change the elementary capacitance del C is given by minus del I is equal to C del x dou V by dou t. As del x is equal to 0, dou I by dou x equal to minus C dou V by dou t. Note, the negative signs equations are due to diminishing V and I, eliminating I and V. Between the partial differential equation we get respectively dou squared V by dou x squared is equal to LC dou squared V by dou t squared. Dou squared I by dou x squared is equal to LC dou squared I by dou t squared. From the equation 3, we can write the 1 by LC dou squared V by dou x squared is equal to dou squared V divided by dou t squared. Equation 4 also called travelling wave equation. Solution. The solution of this equation V is equal to F1 x plus V of t plus F2 x minus V of t. It can shown that the above from satisfy the solution of the travelling wave equation, we can write the second term equation fifth is termed forward travelling wave since x minus V of t constant, which means when t increases, x increases too. Del x equal to V del t. Verification of the solution. Dou I by dou x equal to F1 x plus V of t plus F2 x minus V of t. Dou squared V by dou x squared is equal to F double dash x plus Vt plus F2 double dash x minus V of t. Dou I by dou t is equal to V F1 x plus V of t minus F2 x minus V of t is equal to dou squared V by dou t squared is equal to V squared F1 x plus V of t plus F2 dash double dash x minus V of t. From the second derivative terms, we see that equation from V is satisfied. Note that form F1 and F2 are unspecified, but we have assumed that the first two derivative exist. Forward travelling voltage wave. In forward travelling voltage wave, first of all, forward voltage it will be represented for x1, x12, then x-axis is equal to x2, that means distance, then y-axis it will be mentioned for voltage, then the x1 is it will be represented for the original travelling wave, then next forward travelling wave x0. The forward travelling waves is the inductive reactance value in between the change in the distance value, then Vf bracket T1 plus delta t. That means change in the time forward to the travelling wave in the signal. The next one, backward travelling voltage waves. Then y-axis it will be represented for backward voltage and x-axis is represented for the distance. Then forward x1 is the forward direction to backward direction to the traveling in the distance from original wave. Then x2 is the original traveling backward waves to change in with respect to time Vb t2 plus del t. That means the change in the time with respect to backward traveling waves. Traveling waves continue the wave equation from the current wave accompanying the voltage wave is given by the dou I by dou t is equal to minus L dou V by dou x is equal to minus 1 by L f1 x plus V of t plus f double dash f x minus V of t. Integrating with respect to t, then I is equal to 1 by L into 1 by V. f1 x plus V of t minus f2 x minus V of t is equal to root of L by C bracket minus f1 x plus V of t plus f2 x minus V of t is equal to z0. Then f1 x plus V of t plus f2 x minus V of t. Note, the negative bound backward traveling voltage and current wave opposite sign V2 divided by I2. That means minus z0, where 2 denotes the negative x bound waves. Positive bound forward traveling voltage and current wave are of the same V1 divided by I1 is equal to z0, where 1 denotes the x bound waves. Traveling wave equations, various combinations for forward and backward wave traveling. Here, first of all, represented for the voltage wave, positive x bound or forward traveling, negative backward traveling waves, it will be represented by the current wave. Origin of backward wave. In our discussion, generator is connected to the left end of the line. So, as a traveling wave moving away, forward wave from the generator understandable. However, one would about the origin of the backward, there is no energy sources at the right hand of the line. The only possibility then the forward wave reaches right end of the line does not find correct conditions for transferring the field power to the load impedance. The part of the energy then gets reflected from the load, which results into backward wave. The strength of the backward wave then should be related to the load impedance within which the line is terminated. Since the forward wave carries a energy towards the load, we call the wave incident wave. The backward wave which is carry reflected energy from the load is called reflected wave. The derivation of V and I combination relationship. First of all, input side it will be represented by the capacitance. Then transmission conductors are represented by the resistance and reactance of the element in the transmission line. We can derive the following relationship: dV is equal to I into Z dx. dI is equal to original voltage to change in voltage, V plus dV, Y dx is equal to V. Y by dx equal to x dx is equal to Z into I, then dix divided by dx is equal to Y into V. Setting up a second order equation, dvx divided by dx is equal to Zi, dix divided by dx is equal to Y of V. We can rewrite these first order differential equations in the second order system equation. D squared V by dx squared is equal to Z di by dx equal to Z y V. D squared V by dx is x squared Z minus Z y V is equal to 0. The relationship between the voltage and current combination will be continued. Define the propagation constant sigma s. and then sigma is equal to z yz is equal to alpha plus j beta, where alpha attenuation constant, beta the phase constant. Use the Laplace transform to solve the system has a characteristics of the equation s squared minus alpha squared gamma squared is equal to s minus gamma plus s plus gamma is equal to 0. The equation of for voltage, the general wave equation is equal to v of x is equal to k1 is equal to e power gamma x is a plus k2 is equal to e power minus gamma x, which can be rewritten as v of x is equal to k1 plus k2 is equal to e power gamma x plus e power minus yx divided by 2 plus k1 minus k2 is equal to e power gamma x minus e power minus yx divided by 2. Let k1 is equal to k1 plus k2 and k2 is equal to k2 minus k1 minus k2. Then v of x is equal to k1 e power gamma x plus e power minus gamma x divided by 2 plus k2 is equal to e power gamma x minus e power minus gamma x divided by 2. Here that is equal to k1 is equal to cosecant del x gamma x plus k2 sin gamma x. Traveling wave constants. Interaction of the two traveling waves in the opposite direction approaching, the first of all representing for the approaching, then next of all the combining the resistance and reactive combined process in the wave signal, then next of all in the passing. So the forward and reverse traveling, backward in the equation for derivative in the wave equations. Thank you.